So you're going to have a double bond to the oxygen there and then single bonds to the hydrogen. So 3 groups. Don't forget a double bond counts as a single group. So 1, 2, 3. So we're looking at this guy, right? Separated by 120 degrees, but all in the same plane. So 3 things in a plane, we call it trigonal planar. And because there's no lone pair on the central atom, the name of the geometry is also trigonal planar. So I'll just switch over real quick to the simulation and we'll do that there. So it looks like this. And especially as we get into the more complicated ones, the more you can picture them, the better off you're going to be, particularly if when we start doing polarity. So what's today? Wednesday? So on Friday, we'll start talking about not just as a bond polar, but as a molecule polar. Because if you have multiple polar bonds, it really depends on how they're arranged in 3-dimensional space, whether or not they'll behave, whether or not the molecule will behave like it's polar. Okay? Yeah, question?
I noticed like it started getting, the ones that have no pairs, or no lone pairs have started becoming obvious.
Good.
Like I noticed the ones that like have like 2 lone pairs, you have to do a little bit of mental juggling in your brain.
Yeah, exactly. Yeah, so I think we have one in there that has 4 groups and 2 lone pairs, and that's when you have to start like picturing, okay, what does 4 groups look like? Now take away one, now take away another, and it does start to get really complicated. So we are adding 5 and 6 to this today. I realized in my other class, there's like kind of a cheat sheet I give on the exam equation sheet. I need to look at it and see how much information I decided to actually give you, but that'll help a little bit with that. Okay. All right, next one, CO2. We've done the Lewis structure before, but let's make sure we talk about the geometry as well. Did anyone not get the roll yet? Did you guys in the front get it? You didn't? Are you Nate? Okay. Okay, so the Lewis structure, once you have that, I think this is one that's going to become pretty clear as long as you're remembering that the double bond behaves as a single group, okay? Because 2 groups, the furthest away they can be is in a straight line, so that's going to be linear and 180. And we never really talk about things that have, like, we wouldn't talk about something like this, you know, I don't know, like that. Like CO, there you go. We wouldn't really talk about the shape of that because you really need 3 points to be able to define an angle. So we won't really ask you about shape of something like that. Okay, so this one, I think thinking? Yeah, we can do this one. We'll spend a little bit more time on these because the Lewis structure is a little bit harder. But yeah, we'll go ahead and do this. I'm going to draw this. Let's draw this as CL2F2 instead of CL4. It'll make it more interesting when we come back to it on Friday to do polarity. So still the carbon in the middle.
Last one was linear, correct?
Mm-hmm. Yep. Okay, I'll talk about this note with the Lewis structure in a second. Okay, so I had this question in the other class, and I think it's an important point, is they were like, well, do you have to draw the chlorines straight across from each other? No, it doesn't matter how you draw them at this point because we're representing something that's not planar anymore, right? It's three-dimensional, and so it's kind of irrelevant how we draw it in two-dimensional space because they're not 90-degree angles. They're not directly across from each other. So I'm going to show it to you in the simulation just to prove the point. Okay, so if these two things are the fluorines, I wish I could color them differently, I can't. But if those two things are the fluorines, there's no way for them to look like they're directly across from each other. They also look just like the other two, right? It just depends on which way you turn it. So even if it was like this and it was these two, any two of them are going to be the same in reference to the other two. So where you place them has no bearing whatsoever. As long as you've got two of each, it's going to look identical. Okay? So 4 groups, tetrahedral. Molecular geometry is then tetrahedral as well because they're all bonds. So the angles are exactly 109.5. Only when we add that lone pair in does that change the angle slightly. So I would say these are some of the easier examples that we've done so far. This one's a little bit more complicated, mostly because the Lewis structure just is a little bit, I don't think you guys are going to find it complicated, but it's not one of our more basic ones, okay? So go ahead and do, again, you always have to have an accurate Lewis structure. You can't predict how many groups there are if you don't know exactly how many bonds, how many lone pairs, all of that. So go ahead and draw the Lewis structure for SO2, and then we can think about the shape. So on the Lewis structure, this is just one of those that we have to overfill in order to satisfy the octet of oxygen. Now, technically, you could draw it with a double bond on one of these and a single bond on the other. You'd have to do some weird moving around of electrons, and when you do that, it messes up the formal charge. So there's no reason to not exceed the octet if you're able to. So sulfur is in the third row. There's no reason why we shouldn't exceed the octet. And to keep things, I don't know, not weird, we don't worry about it. We just go ahead and exceed the octet. If you were trying to draw this, I don't think you guys would have even thought to do this, to be honest, because you would have had to move an electron from one oxygen to the other in order to make this work out. And so it just doesn't, I don't think, the way that I've been teaching it, I don't think that you would think to do that. If you did happen to do that, then you would want to compare the formal charge between these two. And this one, so I shouldn't circle the one that's wrong. This one is the one that would give you a formal charge of 0 on everything. But like I said, we haven't ever encountered an issue with having to rely on formal charge because of the way that we've been approaching it, okay? So I don't think that you would even have the inclination to do that. But if you did, you'd have to look at formal charge, okay? Shouldn't be bothered at all that the sulfur has 5 groups surrounding it. That's just fine. Sorry, not 5 electron groups, 5 sets of electrons, right? So 10 electrons total. The number of groups it has is 3, right? If we're talking about shape. So double bond counts as 1, this double bond counts as 1, and then the lone pair. So it's still trigonal planar, right? But it's trigonal planar with a lone pair. So the shape is bent, okay? And it's almost 120 degrees, but remember this guy takes up more room. I should hold my arm like this or something. So this guy takes up more room, and so it just squishes that angle down just a little bit. Okay, so just a little bit less than 120. So trigonal planar for how the electrons are arranged, but bent for how the atoms are arranged. You're like tracing the shape of the atoms. The electron is there, it's influencing the shape, but it's not part of the shape because there's no mass there. So let's look at it on the simulation too, just to make sure that we're good with this. Okay, so, one of those is a double bond. All right, so it looks, or no, both of them were double bonds, huh? Oh, there we go. All right, it looks like this. So if you're doing it like the way I was standing, it was like this, okay? So the double bonds are not straight across from each other. They're at an angle. And this says 120, but remember that's just because it's the model. Either you got to use a real molecule, or you need to just remember, and this is probably what I would say the preference is, because you might not have the right real molecule. Just remember that that lone pair is going to squish those bonds down just a little bit because it takes up more room. All right, any questions on this one? Yeah.
So in terms of the bond angle, it would be a straight 120 if it had not had a lone pair.
Right, so if it had been, and I can't remember if we have another example like this, but I'll just throw this one in. So if it had been that, then it's 120. Yeah, because they're all going to take up the same amount of
Because
space.
the lone pair, it's less than 120.
Yeah, because the lone pair takes up more room. So it kind of pushes down on the angles and squishes them together. Yep. All right. Just seeing where we're at. Okay, good. I think we're making good time. All right, SO3 2 minus. Another maybe slightly harder Lewis structure. It's good practice though. This is one of those chapters, one of those units that I don't think you're going to forget stuff from chapter 10 because we just keep using it. Okay? If you haven't already, probably a good idea to do the Chapter 10 practice exam. Just kind of get yourself ready for the exam that's next Friday, so a week from Friday. Okay, so SO3 2 minus. Don't forget that 2 minus when you're drawing the Lewis structure. Okay, so once you have a Lewis structure, go ahead and check against mine. Again, so I added the 2 extra electrons in green. Remember, when there's that negative charge, they just kind of appeared from nowhere. We don't care where they came from, but they are now part of the structure, so you need to just add them on there. Another thing that's interesting about this one is that it does have resonance structures. Because you have 3 oxygens that are all equivalent, they're all bound to the sulfur, there's really no difference between them. We need to show that the double bond, really what we're saying is spread out over all 3 of those oxygens. But the way we show it is by showing all 3 versions. And this is the resonance structures. Now, this doesn't have any bearing on how we describe the shape because number 1, a double bond and a single bond are equivalent in terms of how much room they take up. So it doesn't matter that this one is technically has a bond order of 1 1/3. That's not relevant for how the shape is going to change. So really you just pick one of them and look at the shape of one of those, and that'll be equivalent for the others as well. Just give you guys a second to catch up with that if you haven't yet, and then we'll look at the shapes. Okay, so 4 groups here. The sulfur is overfilled again, not a problem, okay? One of them's a double bond, 2 single bonds, and a lone pair. So 4 total groups. So I know off the bat, before I even look at the shape, right? If it's 4 groups, the electron geometry is tetrahedral. The bond angles are gonna be somewhere around 109.5. We don't know exactly because we haven't thought yet about the lone pairs, but they're gonna be close to 109.5 simply because there are 4 groups, okay? Now let's look at the shape here. Okay, so 4 groups, like we would expect, that same tetrahedral shape, one of which is a lone pair. So it's, when you kind of turn it on its side, it's that trigonal pyramidal. And then again, lone pair on the central atom squishes those bond angles just a little bit, so we say less than 109.5. If you really care, it's like 107 typically. But this really changes with every atom, really. So those amounts of changes, we just want you to know it gets smaller. So molecular geometry, trigonal pyramidal. Bond angle slightly less than 109.5. Okay, one more before we get into the 4 and 5 groups. So H2S will be our last one here. I'll leave this up in case you're still looking at it, but you can go ahead and start on H2S if you're ready.
I think you said we had to write that structure 3 times.
Yes, showing that the bond angle is moving. Yeah, or that the double bond is moving. And really it's not moving, it's all 3 of these structures averaged together, all of them at the same time. Okay, so doesn't matter which way you draw this. Again, you can't properly represent it 2-dimensional when it's not. This is really similar to water, right? Water, oxygen and sulfur, are very same number of valence electrons. So water looks really similar to this. I prefer to draw water like that because it's not 90 degrees, those angles. But when I draw them straight across from each other, that makes it look like they're straight across from each other. And they're not. They're in a bent shape, okay? It doesn't matter though. You should be okay with the fact that either one of those is not a perfect description. And you need to have in your head what it actually looks like because, you know, that's going to affect the properties of water if you think that it's straight across from each other. Okay, so 4 groups, 2 lone pairs, 2 bonds. We'll switch over to the, similar to what we have here. Let's swap out one of those for a lone pair though. Okay, so still 4 groups, still that same, let's see, how do I usually line this up? Like that. Same basic tetrahedral shape, but now 2 of which are lone pairs. So bent is the term we use to describe that, and we would say less than 109.5. So it's even smaller now than the trigonal pyramidal one would be. So I'll put that over here. So electron geometry, still tetrahedral. The molecular geometry is bent, and those angles got reduced even further than they were in the previous example, since there's now 2 lone pairs. These ones are like 104, if you're curious. Okay, I'm not sure why I put SF6 next, because that's 6 groups, and I would think I would want to do 5 groups first. Let's see. 15 minutes. Tell you what, I'm just going to toss another one in there. There's a blank slide here. Let's do PCl5. Okay, so same thing. Go ahead and draw the Lewis structure, and then once you do, switch over to the simulation and try to build it there and just take a look, and then we'll talk through it. Okay. Okay, so as you finish up the structure, go ahead and check it with mine. Ugh, I'm going to have to not be lazy. I am going to redraw these so that they look, you know, nice and tidy. It's just annoying because then I have to go put on those lone pairs. This is why one of the lab instructors at least gets lazy and just draws them as lines, which is not untypical. I just think it's confusing for you guys. Maybe if I make that a little bigger. Okay. So that's what PCl5 looks like. the 5 chlorines are bound to the phosphorus. No lone pair on the phosphorus, just 5 single bonds. Okay, so good example for us to look at what 5 equally spaced things look like around an atom. And this one's probably the weirdest of all of them because the angles aren't the same between every atom.
Let me guess, is this octahedral?
No, but we're almost there. This is trigonal bipyramidal. So 3, 4, 5. Okay, so look down the middle this way. There's a trigonal planar that's kind of in the center of the molecule. So those bonds are 120 degrees away from each other. But then if we tip it down, we've also got 2 bonds that are perpendicular to that plane. So those ones are 90 degrees away from the plane. So when we talk about bond angles, it's not appropriate to say 90 or 120. We need to say 90 and 120, okay? Because different atoms, are going to have different bond angles. And that's just the nature of dividing 5 things evenly amongst 3-dimensional space, that's what's going to happen. Okay, so it's called trigonal bipyramidal because if you think of the 3-sided, trigonal planar, and then you create a pyramid with the thing up top, so that's a 3-sided pyramid, but you also have the thing on the bottom, so that creates a 3-sided pyramid on the bottom. So it's a 3-sided pyramid bipyramidal, so 2 3-sided pyramids. That's where trigonal bipyramidal comes from. So picture a pyramid made from the middle thing, the middle 3 things down, and then the middle 3 things up. Okay, 2 more. Next, let's do SF4. So this is a structure we've drawn before, so if it seems familiar.
Does trigonal bipyramidal have a specific bond angle?
90 and 120.
So it has both?
It has both, yeah. So you have to indicate both. So I know I've written test questions before, which will say indicate the bond angles of this structure, and I'll have like 180 as a choice, I'll have 90 as a choice, I'll have 120 as a choice, and I'll also have 90 and 120, and maybe just to make things nice, I'll say 120 and 180 or something. So it would be 90 and 120. It just depends on which one you're looking at. Yep.
Is the trigonal bipyramidal with both the electron and molecular geometry?
For this one, yes. Yeah. Because they're all bonds, then it would be trigonal bipyramidal for both. Okay, so SF4 has the 4 fluorines, but it also has a lone pair. So this is like our first variation on trigonal bipyramidal. Now, before we look at it, I want to show you guys the chart that you're going to have on the exam equation sheet. So if you scroll down past that blank slide, it's right here. So it does not tell you electron groups. It doesn't tell you names of, kind of the early shapes. What it does do is give you somewhat of a representation of what these molecules look like. And then I give you the names of the really complicated ones. So these are so infrequently seen that I don't find it super useful for you to have to memorize the names. I want you to be able to identify them. Like this is the one we're looking at right now. It's got 4 groups that are bonds and 1 lone pair. So it's, if you look at the table, like the first row, that's if you have 2 groups. The second row is if you have 3. The third is if you have 4, and this is 5, and this is 6. And then you add a lone pair each time as you go across. So this is trigonal bipyramidal electron geometry and molecular geometry. This one is the one we just drew. So this would be trigonal bipyramidal electron geometry. And then I'm giving you the fact that it's called seesaw. Okay? So when there's 1 lone pair, that's going to be its name. So I would ask you what's the molecular geometry of SF4. But you would need to know how to use the table, okay? When we draw them like this, we're supposed to be saying that the straight lines, those are like flat on the paper, 2-dimensional, and then the dashy lines are supposed to be going into the paper, and the solid lines are coming out of the paper. It's a very not artistic way of drawing, I'm sure, but that's the convention that we use. Okay, so let's look at that on the simulation now. So swap out one of these bonds for a lone pair. So you can see there's still those 3 things in the plane, but one of them is the lone pair now. And if you rotate it, look, it looks like a seesaw. Those are like the little legs, and it's the 2 little seats. So the names do have connection to the shape itself. If you're able to visualize the shape, you definitely could get to the name, but I just won't make you go that far. As far as angles, it's still the same thing. Every time you add a lone pair, it's going to squish the angles. So a little bit less than 90, a little bit less than 120. This one's called seesaw. A little bit less than 90 degrees and a little bit less than 120 degrees. On Friday, we're going to do molecular polarity, but we'll keep doing examples of these so that you're seeing them again. You're just also seeing them in context of polarity. Okay, let's look at this last one together so we make sure we get to do octahedral. We've done this Lewis structure before. SF6 just has the fluorines. I'm not even going to write the lone pairs on there. So it's got 6 groups, and what it looks like is this. So it is, let's see, I can't do this with my body. They're literally straight across from each other all the way around. So the angles are all 90 degrees. It's like you've got 4 things in a plane instead of 3 now, and then the up and down ones. So they're all equivalent to each other. They're all equally spaced around there. We call it octahedral because when they say hedral, they're saying make a shape by like creating a plane on every 3 points. If you do that with this shape, you'll end up with 8 sides. So the 6 things pointing out, think of like, trying to think of something that, a dice is 6 sides, never mind. Okay, so if you were to draw a plane on each of these sides, you would get an 8-sided thing. That comes from having 6 things sticking out, though. Okay, that's why they call it octahedral, even though it's 6 groups. And then we could go on and like add lone pairs one at a time. You'll do plenty of that in your homework. We'll do some more of it in class, but you know they do get pretty complicated, which is why I gave you the names. So, okay, we'll pick up there on Friday. I'll go ahead and write this down just in case anyone's keeping track.
Can I ask you a question?
Yeah.
I just can't find the practice test on the.
Okay.
Let's see.